Why does a moving skater tend to continue moving? The short answer to that question is that an object in motion tends to remain in motion. In other words, if a skater is moving and you leave that skater completely alone, you don't push on him, then that skater will continue to move. This behavior is actually the other half of inertia, and it's how objects in our universe work. The complete concept of inertia, then, is that an object at rest tends to remain at rest, and an object in motion tends to remain in motion. It's time to demonstrate the second half of inertia using a banana. This experiment is designed to test the inertia of a moving object. I'm going to throw the moving object, a banana, to the right, and it's going to have a close encounter with a very sharp knife. Now, I'm not going to be holding the banana when it meets up with the knife. So, if anyone asks you after the fact, who killed off that banana? It wasn't me, officer. The banana did it itself. So the banana is going to be a moving object, and it's going to tend to continue moving. That's its inertia. So here we go. I'm not going to be holding the banana when it gets to that knife. It's on its own. Ready? Get set. Sliced banana. Let's see. Can I find part of it? Well, I got half of it. The rest, it's on the run. So there you have it. An object in motion tends to continue in motion, even if it encounters things like sharp knives. The motion of an inertial object, that is, an object that's free of external forces, is very simple. It moves in a straight line at a steady pace. But doesn't that neglect an object at rest? No, because an object at rest is just a special case of steady pace motion. It's steady pace motion where the steady pace we're talking about is zero. We're ready for a formal statement of the concept or principle of inertia. Because we don't know all the words for some of the physical quantities involved, we'll consider this a first draft. It's known as Newton's first law of motion, and it states that an object that is free of external influences moves in a straight line and covers equal distances in equal times. Skating is full of examples of Newton's first law. Off I go! I'm coasting! Whoa! Good padding! To perfect our first draft, we need to identify those external influences. And we need a better way to describe motion in a straight line that covers equal distances in equal times. Still, we're making progress. We can already use Newton's first law to figure out if an object is experiencing external influences. If that object is not traveling in a straight line, or if it is not covering equal distances in equal times, then it's not inertial. It's not obeying Newton's first law, and it has external influences. For example, if I skate into that cabinet, then I'm not obeying Newton's first law. The cabinet influenced my motion. A skater who is heading straight north at a steady speed is inertial and is obeying Newton's first law. That skater is traveling in a straight line path, namely northward, and is covering equal distances in equal times. Skaters are inertial much of the time and are moving according to Newton's first law of motion. In a word, they're coasting.